All right, good afternoon. Thank you all for coming out and joining us. This afternoon, we're going to talk about the visible network, how Netflix uses Kinesis streams to monitor applications and analyze billions of traffic flows. I'm Alan McInnes. I'm a solutions architect at AWS. I am just the opening act. I'm not going to be up here for too long. Just going to do a few introductory pieces. And then John Bennett from Netflix is going to walk you through in detail the specific use case. What I'm going to do before we hand it off to Bennett here is just talk about streaming data in general, kind of general terms, talk about streaming data, talk about some of the services in AWS that many customers are using to process streaming data. And we're going to talk about what we're calling the decision latency. And so what I mean by that, if we take a look at this slide, we've got a train. Let's assume it's like a Hyperloop train. It's very fast. And we've got a cargo ship, right? One's fast, one is slow. In your business, when you're talking about making decisions about anything, it could be things like, how do I optimize my products that I'm showing on an e-commerce website? How do I know operationally if my systems are running successfully? These are things that if you can answer questions about them quickly, you can make changes and make optimizations that better improve your business operations, better improve things for your customers. So that's what we mean by decision latency. So when we look at the value of data, we talk about what is important, how does it become more valuable? If we look at this chart, and this is from a white paper that was published by Forrester called Perishable Insights. It's a good paper that talks about the value of data over time. If we look at the far right of this chart, this is pretty traditional batch processing. We're talking about data that you might review on a daily or weekly basis. So there's certainly value in that to you and your business. However, it's old, right? It's a week old. It's not going to tell you whether your website, as an example, is operating successfully right now because it's a week-old data. If you have to make time-critical decisions, you want to know what's going on immediately. And that's to the left side of this chart, the time-critical decisions, things that you want to make decisions on in seconds, maybe up to minutes. And so recent data is valuable if you can act on it in real time. So you have to capture the value of your data. And so on AWS, we have a set of services that make that pretty simple. They're Kinesis, Amazon Kinesis. Quick show of hands, how many folks in the room are either familiar with or already using one of the 3 Kinesis services in your systems today? Pretty good. OK, so I'd say it's about maybe, I don't know, maybe a fifth of the room. So I'm not going to spend too much time going into details about the services. I know you guys just want to hear from Bennett and how Netflix is solving some problems. But to set a little bit of context, I'll talk about the 3 sets of services. I think it's good to understand that, I know that Bennett's going to talk primarily about streams, but there are 2 other services that comprise the Kinesis suite of services. So Kinesis streams, generally you'll use this when you want to process, custom process your data. So you have a streaming set of data coming in. You want to apply some custom processing to that data, and then send that data further downstream, either into a database or into S3 for storage, or maybe onto another stream so you could do some chained processing. But basically, with Kinesis streams, you're going to write some data producers, and you're going to write some custom code to do the data consumption. That's streams, and Bennett will talk a lot more about how they use that. Firehose, while it is a streaming service, the idea behind Firehose is let's just make it simple for you if your end game is just to take your streaming data and persist it somewhere. You're not doing a lot of data transformation, although you can do that now with Firehose. But if your end game is just to take my streaming data and persist it into one of 3 destinations, today those destinations are S3, Redshift, and Elasticsearch Service. So those are 3 services in AWS. If your end game is just to take your streaming data and put it into one of those 3 services, Firehose is the tool for you. There's no code you have to write to do that. It's all a managed consumer is the easiest way to think about that. Think of it like a managed consumer on a stream. It's going to take the data, buffer it, put it into the destination, and it's also going to have the built-in retry mechanisms and failure scenarios, that kind of thing. The third service is Kinesis Analytics. So the nice thing about this is whether you're streaming your data through streams or you're streaming your data into Firehose, if you want to get some insights into that data right now, like how many times has this event occurred in the past 5 minutes? Kinesis Analytics can do that for you very simply by just writing some SQL. So SQL, I'm guessing many of you are very familiar with SQL. By writing a simple SQL statement, using Kinesis Analytics to run that SQL against your streaming data and get results as soon as that window closes. So like I said, I've got real-time streaming data. Every 5 minutes, I want to count some kind of an event, and I want to spit that out so I can make some business decisions about it. That's where Kinesis Analytics fits in. Simple to use a SQL. So with all of this, with Kinesis Streams and Kinesis Firehose as your front end, we kind of have the full flow of data, right? We ingest, we process using some Amazon Kinesis-enabled application, and here we have a library called KCL. I won't bore you with the details of that. It's a library that you can use to process streaming data. We have Lambda and Kinesis Analytics that are your processing, and then we have good integration with other AWS services. So we have the full flow of data from ingest to process to react, and then, of course, to persist your data. So if we go from left to right on this slide, we've got a number of services where maybe we're ending up, apparently we have a connected scooter that's sending its data to a stream, and we might do some real-time processing and end up the data in S3 or maybe Redshift, so I could do some BI on it. So Kinesis acts as the front end of the streaming data, and nice integration with a number of different AWS services to help you process and react and take action so that your business can learn something about what's going on immediately. So who's using Kinesis today? A number of different customers. I'm not going to talk about all these in detail, but let's just quickly talk about maybe like Sonos. Probably many of you are familiar with Sonos, the connected streaming audio speakers. So they run real-time streaming analytics on data that's being sent from all their devices. MLB Advanced Media, another good customer. So they stream 17 petabytes of game data, MLB, Major League Baseball game data. And then lastly, I'll talk about just quickly about Hearst. So Hearst analyzes 30 terabytes of clickstream data through Kinesis. So Hearst, if you're not familiar with them, they are a large kind of publishing and media company. They own hundreds of different magazines and websites for TV channels. They own newspapers. So a very large company that owns a lot of media properties. And anytime, you might not know, but if you're on a website that's owned or run by Hearst, right, the clickstream data is being used to determine which articles are successful, which ones should I promote. All that data is being streamed through Kinesis, and they're using Kinesis to make decisions in real time about what they can do better to improve the content on their website. And so why do these customers choose Kinesis? I'm not going to touch on every point, but I'll talk about what I see when I work with customers is one of the main reasons they choose Kinesis is, one, lower costs, and two, kind of a combination of the increased agility and the ability to scale very simply. So there's other products in the industry that you could use to stream data. Kinesis is a managed service, particularly Kinesis Streams. Very simple. I want to create a system that's streaming in data from my applications. A couple of clicks, I get a stream, and I can start streaming data into the system within like 5 minutes of starting it. No system, no EC2 instances to manage. It's a fully managed service, and so those are some of the main reasons that we see that customers take advantage of this. Is its simplicity, the agility that you get from using it, and of course it can also lower your costs. And so we talked about a couple of customers. Before I hand it over to Bennett here at Netflix, so they're using it, like I said at the very beginning of the title, right, to stream billions of network traffic flows in real time. And so they do this because they obviously want to get some real-time insights into what's going on across the Netflix set of infrastructure that's running on AWS. So they stream a lot of data, get some real-time insights into what their applications are doing. And so to talk more about how they do that and what they're doing, and to talk about what is Netflix's decision latency, I'd like to introduce John Bennett from Netflix. Thanks.
Thanks, Alan. So what I thought I'd talk about during the rest of this session is, what kind of problems Netflix faces when it comes to monitoring applications. And the solutions that we came up with, evolved over time. Just like many of you, we do a bunch of trial and error. Most of it doesn't work. So I'm hoping to maybe kind of provide a little bit of guidance from our experience to help you solve similar problems in your domain. We're going to be looking at analyzing network traffic as an example, but really, these techniques are broadly applicable. They may be used in, say, like a financial domain or e-commerce. It's essentially able to be used in a general sense. And in particular, I'm going to talk about how we use Kinesis in almost all of our solutions. And then finally, we'll kind of review some of the results that we came up with. So for folks that don't know, Netflix is big. We have over 100 million subscribers. We're spread across the entire world. And every day, we're getting bigger. So under the hood, we use dozens of accounts. We're spread across multiple regions. There are hundreds of microservices that are working in concert to make Netflix better. And all of those are deploying production changes every day. And at the same time, they're scaling up and scaling down in response to changes in load. And in the end, we end up with over 100,000 instances. And that doesn't include all the containers that are running underneath. So like any other complex system, things break, right? And one of the more convenient scapegoats when, say, like a systems engineer or an application developer can't figure out what went wrong, it's almost always, right, like, what's wrong with the network? Just blame that. It's really easy because in a lot of ways, we lack tooling to really tell us whether or not the network was a problem. Even earlier today, I think there was an issue in US East 1 where we weren't actually able to tell, like, hey, is there actually a connectivity problem or is it our own systems? So we can try to figure out a way that network engineers talk about reducing this thing called mean time to innocence, which essentially is like, how do we tell everyone that it's not our fault, right? And then another question that we see is, why is the network so slow, right? I'm expecting things to happen within like a couple of seconds. But really, one of the more tricky things to figure out is, are you actually following this optimal network path? You know, it may seem very easy to figure out, but in a complex system, that problem can be several times more complicated if you're using dependencies that you're not familiar with, or dependencies that are changing underneath you and may actually be taking a suboptimal path. So we'll be talking about how we end up monitoring that. And lastly, my service can't connect to whatever. It's surprisingly difficult to get any application developer to tell you comprehensively, give me a list of all the things that you need to connect to, right? Because they may understand that, hey, I need to talk to service A and service B, that's it. But maybe there's a bunch of things that it needs to connect to during like startup, or maybe there are things that are making subsequent connections, and maybe they have no idea. So even in a distributed system, we're making decisions about how to enable all of these different network paths and making decisions on whether or not this should be allowed or not allowed. And if we don't know what dependencies each application needs, then we're kind of just shooting in the dark, right? And so part of the reason why we're looking to analyze network traffic logs is that tells us exactly what applications need to connect to. So the list of challenges are very long when it comes to doing this in the network, the Netflix ecosystem. One, we have no access to the underlying network, right? That's AWS's job. That's why we pay them. But at the same time, our traffic volume is huge, right? Logs of network traffic ends up being gigabytes per second, right? Billions of flows every day. And at the same time, these logs end up being things, it's a log between two IP endpoints, which isn't necessarily all that meaningful to us, right? IP addresses are very ephemeral. They could be attached to an instance for a minute, a day, a year, and they could be changing every other second. So really, they're randomly assigned, it's unpredictable, and in a way, really what we want to do is map this information to some longer-lived logical group. And typically, when you want to analyze network traffic, and you're in a data center, you would use something like SFlow or NetFlow. But in AWS, they actually provide this great API for us that tells us, hey, these are the kinds of network traffic that you're seeing in your accounts. It's called AWS Flow Logs. It's good. It covers all the traffic within the VPC, and it gives you a single point to read, and it has all the core information that we need, like source and destination IP. But like everything else, right, it's not perfect. There's this 10-minute capture window. So essentially, a flow could happen in your system 1 second, but maybe you don't see it in a VPC flow log for 10 minutes. Right? That doesn't really help us have a very real-time based system. And at the same time, these logs are stateless. So they don't tell you whether or not this was a request or a response, and that's really what we care about. So we'll get back to that later. So again, I'm talking about examples where maybe a flow is between one source to a destination at a given time, right? IP to IP. Who knows what those IPs mean? But really what we want to get to is, hey, this is the source metadata to the destination metadata. I know that service A is talking to service B. This is the account it was in. This is the zone. Now I start to have a better insight into what's actually happening in the system. So our goal was to build this new data source that we can actually use to do an analysis of our network traffic. We knew that it needed to involve multiple dimensions like accounts and regions and zones, but it also needed to have Netflix-centric metadata like, hey, what application is it, or what cluster is it? And we wanted to be able to do fast aggregations, right? This is not something that I want to submit a query and check back in a couple of hours after lunch. At the same time, we don't know what kind of queries we actually want to run. We can try and predict, but we're almost always guaranteed to do that badly. But if we sort of make sure that the system can do this sort of ad hoc querying, then we can slice and dice the data however we want. In the end, what we want to do is we want to add visibility to the network, right? We want to go beyond, hey, these bits are traversing between these two IPs. We want to know, hey, these two applications are communicating. So that's why we built Dredge. This is our internal tool. And what it does is it enriches traffic logs and then aggregates based on this dimensional data that I was talking about. Now, Dredge has evolved in a lot of ways. One, because there were so many questions that we had no idea what the answers were. How much data is actually generated in the network, right? What would it actually take to do that in real time? Is it worth it? So what I want to discuss now is some of the patterns that we've applied unknowingly and then knowingly to sort of tackle this large volume of streaming data so that we can actually figure out how do we actually derive this meaningful information. So just a quick overview, right? We're starting off with these raw VPC flow log events, right? They're the communication between these two IPs. They're going to get processed in some sort of way, and what we want to come out of that system is this enriched version of the flow log, right? Two IPs now these are the actual source and metadata behind those. Now, the first step that we tried was batch processing. And Alan discussed this a little bit earlier, when you can use Kinesis Firehose. This is a totally reasonable way to start, right? There's no need to take on the burden of doing things in real time if you don't know if it's even worth it. But most batch systems will have this sort of interval that you need to work on this amount of data. Typically, they do this every day. So for us, we started off having our interval set at 24 hours. Now, the important characteristic about batch processing is that essentially you're going to be processing a fixed amount of data that's not changing, and the way you measure yourself and whether or not the system is working efficiently is how fast you can crunch through that. Now, there's some limitations to that in that as we're reading these network traffic logs, right, these IP to IP communication, we need to reach out to some sort of data source that's going to tell us what those IPs mean. So we may need to reach out to some remote database, or maybe we put a cache in front of the database to make it faster. Or maybe we even bring that database locally to the batch processor to get rid of the network round trip time. And we'll go through these limitations in more detail. So, here's how an architecture might look if you were going to do it in batch. Right, we're taking in these VPC flow log events, and instead of doing it in real time, we're actually going to send them directly to storage. So now that the flow logs are sitting in storage, At the same time, we have this source of metadata changes, right? Whatever that ends up being. In our case, we're polling AWS APIs and also using our internal systems. And we were sending that metadata change to an external database. So when the batch processor kicks in, it says, hey, I'm going to grab whatever the recent amount of data is in storage. I'm going to cross-reference it with our metadata, and then I'll pump out these enriched flow logs. If you want to do this using AWS tools, you could end up using Kinesis Firehose. So you can take that stream of VPC flow logs and dump it into some like S3 bucket. Right? You can use Lambda to do the batch processing at some given interval. And I don't know, we ended up using DynamoDB to store metadata. So again, total reasonable way to start. But like I said, the big characteristic, right, of batch processing is this delay. Right? Are you able to withstand some 24-hour delay on when data is happening between the time that you can actually get value? You know, that's not exactly acceptable for us because in 24 hours, our systems are completely different. So, you know, what use is that? So here's where we're going to spend a little bit more time. When we're doing stream processing, right, the delay is much, much lower. In our case, we were able to get it down to, say, 5 to 7 minutes. But really, that 5 to 7 minutes is actually because of the capture window that I mentioned a little bit earlier from VPC flow logs. Right? Those are being provided on every 10 minutes. So really, if you wanted to do it we could be actually doing this in real time if those were provided in real time. But the big difference between stream processing and batch processing is now you have no idea how many events are going to occur within some given window, right? Because you're operating on them as they happen. And in this case, instead of measuring by throughput, really what tells us whether or not we're operating on the stream efficiently is how far behind are we from the very head of the stream, right? Are we keeping up with it, or are we falling behind? A lot of you will be familiar with like this producer-consumer pattern, right? Is the consumer keeping up with the rate at which data is being produced? And they have the same limitations as batch processing. You can use some remote database, you can use caching, or you may even bring that database closer to the processor. But let's dig into a little bit more detail. So instead of batch processing, we're going to do stream processing. But one of the big problems when you're going to be interacting with some remote database is now you need to actually bridge this gap between the rate at which your raw data is being produced and the rate at which you need to actually query this external database. So let me try to back it away from like the network example. Instead of VPC flow logs, say it was sensor data from that internet connected scooter. Right? Say that was the sensor data, and you actually needed to marry it with like environmental readings. Or say instead of VPC flow logs, it's a log of, I don't know, financial transactions, and you need to marry it with some other rate in order to figure out what the actual transaction looks like. That's what would represent these flow logs and this metadata. But the problem becomes when this rate of VPC flow logs could be millions and millions per second. Right? That means that for every flow that comes into the system, you would actually have to query the database at that same rate. And that's definitely going to be no bueno, right? Because now you're talking about millions of queries going to a single database, and now you're going to have resource contention. And you can even run your queries in parallel, and that's just going to totally overload the database. So typically, when you run into those problems where you're trying to bridge a gap in performance, you'll go ahead and put a cache in front of it. And actually, I'll go through that in just a little bit. But instead of using Kinesis Firehose, we can use Kinesis Streams, and we'll do this custom processing on the stream instead of dumping it to S3. Right? At the same time, we're still taking those metadata events and we're pumping them into DynamoDB. So we're going to read from the stream, and we're going to, at the same time, query this remote database. But if things are slow, we can put a cache in front of the metadata database in order to improve our read performance. These are things that are very typical, right? In that if you need to allow more reads than writes or something like that, hey, you need to maybe create an index or a secondary index or put some sort of cache in front of the DB layer. Very common. And if you wanted to do this with AWS, you could use their own like Memcache D and then still use DynamoDB. But the problem with using caches ends up being more problems than it's worth. How do you manage like cache invalidation? Right? Because if you have this cache sitting in front of this DB, in some way you've got to set like a TTL on the items in that cache. If it's too low, then you're always going to be getting cache misses. So you might as well just like ditch the cache. If the TTL is too high, now you're going to be getting stale data every time you hit that cache. And then it's up to you on whether or not that risk of joining with stale data is worth it. In our case, it wasn't. So one of the insights that a gentleman named Martin Kleppman writes about in some of his blogs and a book that he put together called Data-Intensive Applications is that these database indexes, caches, materialized views, these are all derived data that we use in order to speed up read performance. Right? They all come from, they're all sort of hidden away from us. You know, when we have some sort of database, a database is receiving like a stream of changes, but really when you query the database, you're just getting that fixed snapshot in time. So there, under the hood, there is a stream of changes. It's just completely hidden from you. But these indexes that come from building out this, the database can be derived from this original stream. So what he proposes is why not just expose that stream of changes directly to the user, to our applications, instead of having to create some cache or using database indexes. And he calls this process change data capture. The kinds of tools that we use to do that ends up being like a log-based message broker like Kafka or Kinesis, and you can use that to send these change events and expose the change log as a first-class citizen. So instead of querying some external database, we would actually consume both streams of data and then do the join ourselves. In a way, you're creating like this alternate view of your data locally so that you don't have to make a round trip time to an external database. And as you're reading both streams, you can update your sort of local view of this change log so that it's optimized for your use case, right? Everybody might do it differently. Let me try to make this a little bit more concrete. So we have these two streams, right? We got VPC flow logs, and then we have another stream of this metadata changes. Really, what we can do is we're reading from this stream of traffic. We can create this customized data structure. In our case, I thought we actually needed to leverage some exotic data structure, some like radix tree or skip list. I don't even know. I'd have to go back and read a book. But really, just a hash map and a sorted list totally worked out fine for us. So as flow logs are coming in, we sort of have this map of, given this IP, these are the metadata that are valid during a different time interval. And every time we get changes in our metadata, we can just update this table. And this is all custom within memory, right? Now we don't actually have to go and request from an external database, hey, you know, I have this IP and this timestamp, can you tell me what that means? You already have this sort of pre-computed cache there locally. So what the final architecture ended up looking like is this. Everything is much simpler. There's just a single stream processor, and you're really consuming from these two streams, and you're doing this join, right? We're doing this, well, stream join, we don't cross the streams. That's a little bit more dangerous. But still, in the end, we're coming out with this enriched flow log where we don't have resource contention, there isn't a network round trip time. Things are totally optimized to our application. And one of the things that you might notice is that we don't actually use Kinesis to do our stream of metadata changes. And I'll explain why that is in just a little bit. But you can see how Kinesis is a constant theme through all of these patterns, right? It's worked out for us in so many ways because it's integrated very strongly with other AWS services, from flow logs all the way to Elasticsearch, and it scales really well. It's stable, and they provide this great library that I think Alan mentioned earlier called the Kinesis Client Library. And in the end, we actually spend less using Kinesis than we would if we were using our internal Kafka clusters. So just to speak to some of the integration points. One of the biggest fears that we had taking on this problem was, all right, there's this crazy amount of network traffic. How are we actually even going to deal with it, right? Who's gonna ship it everywhere? How are we even going to read from something like that? And VPC flow logs and Kinesis can be used together to actually remove the need for you to write any code in terms of producing that data. With a couple of API calls, we could set up systems so that all of our accounts and all of our regions are actually sending their traffic logs to a single Kinesis stream. And that was a huge win for us, because in this whole system, no code on our part to actually take traffic logs and put them into the Kinesis stream, right? Because that's the stuff that we don't actually care about. What we really, really want is we want to read this data. Like, I don't care about writing the data. So this was a huge win for us. At the same time, it allowed us to experiment, right? Hey, can we do it with batch, right? What's involved? It's a very straight setup using Kinesis Firehose, and then we could just fire data into S3 and deal with it later. We've even experimented using Elasticsearch and Redshift, and we had to change maybe 2 or 3 lines of code. That was really, really good for us, because at the same time, we don't even know if this is worth it, right? Because this is a lot of data. And at the same time, there's all this complication when it comes to systems that are being launched to enrich it. So it allowed us to sort of experiment and figure out where's that good balance between our data being processed and data being valuable to us. And then when we were ready to do it in real time, we could transfer and migrate to Kinesis streams. This is a graph of the throughput of our traffic logs over a week period. And you can see it's very, is it sinusoidal? Diurnal? I don't know, okay. Where there's a peak every day, right, and a trough, and that's responding to our traffic load throughout our entire system. And this sort of pattern can be very problematic to other systems like Kafka, but for Kinesis, it wasn't a problem. And even if you look in more detail, every hour, things are very spiky. And that's because VPC flow logs are generated in this very defined 10-minute capture window. This can also cause a problem for things like Kafka, but it wasn't a problem for Kinesis. The Kinesis client library was really pleasant to use, right? It kind of automated all the boring stuff that we didn't care about, right? Load balancing, and then reading from records and checkpointing. All of that is handled because it integrates with DynamoDB. And it provides sort of the stream level and shard level metrics that help us figure out if things are actually working properly. And the last thing I wanted to mention is that this total cost of ownership, that's so low that we haven't really even thought about Kinesis since we started using it. It's handling on its own, it's running, it's managed entirely by AWS. All we need to make sure is that there aren't enough shards for us to be able to do things in parallel. But there are some use cases where Kinesis isn't the right tool for the job, right? If you need to actually have so many shards that ends up being a problem, that could end up meaning that Kinesis doesn't fit, because then you've got to like fan out to some other Kinesis stream or increase the amount of shards in some unreasonable way. But also, one of the things that is a limit on Kinesis is that the farthest back that you can keep data in a stream is 7 days. So I don't know if you remember from our architecture diagram earlier, if we have this stream of metadata changes, that change for, say, a given IP could happen yesterday, it could happen today, or it could have happened several months ago. If you have a stream where you're only able to keep 7 days worth of data, you wouldn't be able to go far back enough for changes that may have happened a lot earlier. So Kafka ends up providing that sort of system for us, and they provide this log compaction mode, which sort of clears away old data in case you don't need it. So let's talk about some of the results. After all that work, right, we're enriching millions of flow logs. There's gigabytes of data per second. What do we end up coming up with? we're doing 7 million flows per second. Every flow that comes in ends up being about 5 minutes old. So that's generally still useful for us. Obviously, if we can bring that down to seconds, it'd be better. But really, all we have is one stream and hundreds of shards. So let's revisit some of the questions that we had earlier. What's wrong with the network? So this is where Dredge comes in, and it helps reduce this mean time to innocence. Right? Is it the network's fault, or is it some application developer's fault? Here's what Dredge can do. It groups things by fault domain. I had mentioned a little bit earlier that with traffic logs, we can break things down by dimensions, like account and region and things like that. We can group things by fault domain, which essentially means, hey, everything in this account, this zone, that sort of is a single fault domain. And we can compare what those connect to on the other side. What account and zone do those services hit? So if, like service A, can't talk to service D, but say everything else in its shared fault domain can still connect on the other side, then that's probably a bad code push, right? You push it back to the developer and be like, you go figure it out, I'm gonna go and take off. But say, for instance, all of those services in the single fault domain all share this degraded performance problem. Then that sort of may be an indication on whether or not there's a network outage. Really, really valuable. Why is the network so slow? My favorite. Because it's trickier than it seems, right? Dredge can actually identify whether or not you're taking these high latency paths. So one of the things that you want to be doing when you're using AWS is you really want to be following what we call zone affinity, right? A service should really try to strive to communicate to other services within its zone. That's going to mean that you're going to have less than like a millisecond worth of latency, right? Minus the time the application takes. But if you go cross-zone from, say, US East 1D to US East 1E, you're going to be adding, I don't know, probably a couple of milliseconds, maybe less than that. And maybe that's not a big deal. But if you've got large volumes of traffic, adding those couple of milliseconds to every transaction may end up being meaningful to you. But here's where the bigger deal comes in, right? What if you're going cross-region? Now we're talking 30 to 300 milliseconds. That can be very problematic. Right? No one wants that, especially if you want your system to be performant. Now, this could be straightforward if you can identify whether or not service A is talking to service B cross-region. But what happens if you're connecting to service B and you're in zone, you're like, I've got it, I'm golden, I'm hitting services within my own zone. But then it fans out to, say, another zone or another region, and now you're still going to be eating this penalty of high latency. And Dredge sort of helps us understand whether or not these high latency paths are being taken, because now we're reading all traffic flows within the network, and we're breaking things down by logical groups like accounts and regions and zones that tell us not only this is the source of traffic, but we understand what the destination is. So this is a really huge win for us in that, one, it helps us understand how we can actually improve the performance of our systems, but also we can actually reduce the cost. When network traffic goes between zones or even between regions, that is several times more expensive than staying within the same zone. So some initial findings is that we figured out that almost a quarter of our traffic ends up being cross-zone, which is crazy. You would think that we had somehow optimized that, but we haven't. In a lot of ways, our systems have evolved so quickly that engineers aren't necessarily thinking about the latency that's being added to the system by doing cross-zone traffic. But even more disconcerting is that 14% of that ends up being cross-region. Some of that is intentional, but some of it is definitely shooting yourself in the foot. Lastly, my service can connect to its dependencies. So Dredge really helps identify what is inbound to a service and what's outbound to a service. Some of our existing tools end up trying to do this with distributed tracing. Some of you may be familiar with Google's Dapper. And this sort of is like understanding what breadcrumbs a request hits along its way through, as it makes its way through the system. And it does this through sampling, but it's very JVM-centric. At the same time, those things aren't necessarily having a lot of coverage, right? If it's JVM-centric, how do you do that for, say, Python or JS or Go? And it has other problems in terms of capturing, say, startup dependencies or protocols other than TCP IPv4. So just to give you an example of one of our, what we found, right? Say service A is actually talking to Cassandra and Memcache D. You're like, that's what my system is. Like, I know because I wrote it. But really, if you actually dig into the network traffic, you find that you're not only talking to that, but you're talking to Discovery, you're talking to a Kafka cluster, you're talking to S3, you're talking to SQS. A lot of these application developers didn't even know that that was happening on their systems because they were more focused on the flows that are under their control versus, say, like a client that they might be using. So we found that there's a significant discrepancy between Dredge and the sort of dependencies that are surfaced by our distributed tracing system. Almost 100% of the services that I sampled found this, this delta between the two. But almost always, Dredge data was much larger than the data that was being produced by distributed tracing. It's consistently underreporting. And we have high coverage now because network traffic doesn't have anything to do with the runtime that you're using, the language, or the framework, right? Basically, if you're using the network, Dredge is going to see it. Also, this is super helpful for us to understand what AWS services applications talk to, because those calls would never be instrumented in a way that would be surfaced to our systems engineers. So security has actually been using this data source very heavily, because now they can understand what applications need to talk to each other, and then they can sort of reduce the blast radius in case those services end up being compromised. One of the long-standing values at Netflix is freedom and responsibility, right? We try to provide as much freedom to our application developers. So say we may open up security groups very wide for everyone to talk to each other. But those application developers may not know how to rein that in. But by using Dredge dependency information, we can sort of reduce that scope and make sure that systems aren't compromised in suboptimal ways. Also, flow logs give us the only source that tells us whether or not security groups actually work. Right? There's no other way to figure out whether or not some security group rule actually rejected traffic on some port or protocol. At the same time, we also understand what applications have an increased risk profile because they're communicating with things on the general internet, either outbound or inbound. So in the end, what I wanted to be able to communicate is that by enriching and aggregating this data, we ended up putting together this really powerful source of information. It can be used for monitoring, for triage, for cost analysis, for security auditing, and it takes this invisible network where we lack tools to actually adding visibility and giving us actionable items to take from there and make our systems better. So that's it. You can actually reach me on Twitter if you have any questions. I think we actually have a few minutes for questions, unless I was talking so fast that pretty much just went over everyone. Hi.
Hey, you mentioned that you're doing join with Kafka. Can you kind of elaborate on that? You're like basically consuming those on one there, or how are you doing that?
Yeah, so the question was, can I elaborate on the joining of the Kinesis stream and the Kafka stream? Yes, that's happening on a single instance. So they're both sort of having the equivalent of the consumer groups, reading from two streams and then doing a join. So the question was, are we using tables? K-tables? Not necessarily K-tables. We're just using just an in-memory map. Mm-hmm. Question? So the question was, what was our experience using Elasticsearch? when we were using Kinesis Firehose, we could send traffic logs to an Elasticsearch cluster, but it wouldn't be enriched. So the data that would end up in Elasticsearch would just be our IP and port information. So it sort of added an intermediate step that we didn't think was necessary. It's like, oh, well, you have traffic logs, that's IP to IP communication. And now it's in Elasticsearch, it's still IP to IP communication. And then we have to take things out of Elasticsearch, do the enrichment, and then ship it off somewhere else. Yeah, so the question is, you can use Lambda now to pick up from either S3 or Elasticsearch. Yes, you can use Lambda to do that. Hi, go ahead.
Yeah, so since you have a EC2 instance that's consuming from both, do you have to like find that instance if it ever was down? Like, do you have some delay on how long you have to wait before you get the useful logs back up and running?
That's a good question. So the term is cold start, right? If you're bringing up, say, a new instance, right, which is all of our applications should be prepared to do that. How do you actually handle that in terms of being able to make sure that you can continue to enrich new data? And our instances end up taking 5 to 6 minutes to read from the very beginning of our streams in order to gather all the data it needs so that it can start enriching new flow logs. So yes, the reason why we would use Kafka to do that is because we can maintain data from the very beginning as opposed to only like the recent, say like the last few days. I think so. Question? That I can answer it the same way. Same question. Just our changes of metadata. Sorry, the question was what data lives in Kafka. So essentially, given some IP at a given time, this is the metadata connected to it. The enriched data we end up putting that into a Druid cluster. It's a tool that was built by folks from Metamarkets. It just allows us to do this like ad hoc queries that we wanted to end up doing in a way that doesn't force us to like create indexes and have like a very small subset of queries that we can ask. Any other questions?
One over here.
Oh, yeah, go ahead. So the question is, I guess, how do we use the KCL, the Kinesis Client Library? We use it out of the box in a way that the documentation provides. They outline an interface that your Java or Scala applications need to implement so that as data records comes in, it processes the data, or it does like checkpointing. It's pretty straightforward, and that was, I would say, that was one of the more, where I was the most reluctant, right? Because if you're going to be reading like this large volume of data from any data source, the client library needs to actually be able to handle all the failures and load balancing. Yeah, but it was actually really helpful for us. Are there any questions for Alan?
That's okay.
No? Yeah, go ahead.
So it's interesting that you chose Druid for your ad hoc query database. Typically, Elasticsearch is also used to design to do that.
So the question is why use Druid for like ad hoc queries and OLAP style queries instead of, say, Elasticsearch? I think when I look at Elasticsearch, I go, hey, do I need full text search? If not, like I think it's probably the wrong fit. But it's definitely something that is usable. Anything else? Thumbs up, thumbs down. Was it okay? Everything was okay? Yeah. Sweet. You guys aren't just saying that? Yeah. Yep. Yeah. The question was, can we use install Druid in AWS? Yes, but it's not without pain. It's like 15 different subsystems. Another alternative that I think folks at Cloudflare use is ClickHouse, which comes from Yandex. Yeah, ClickHouse. A much simpler system, less moving parts, much easier to reason about, right? You don't end up leveraging things like Zookeeper, which is notoriously hard to operate. Yeah.
Yeah, Absolutely.
Any other questions? I'll be outside in case anyone wants to throw things at me or, I don't know, give me candy. No? Okay. All right. Thanks, guys.